This is topic 3.2, implicit differentiation. Before we learn how to find the derivative of an implicit equation, we probably need to talk about the difference between an explicit and an implicit equation. So let me give you an example. An explicit equation is exactly what we have been working with. Y is explicitly defined for. So you could say something like y equals x plus 17. That is what we call an explicit equation. Everything's done for you already. One variable is already solved for in terms of the other. But sometimes we have an implicit equation, and many of these are not functions at all. For example, x squared plus y squared equals 16. Our variables are embedded in each other. They are implicitly defined. And so the good news is we can find the derivative of equations like this without solving for the variable first. So you don't have to go ahead and solve for y equals plus or minus and so forth. We can go ahead and take the derivative right off the bat. Okay? Let's go ahead and talk about our method of implicit differentiation. We will also discuss the chain rule. I think we need to go over a few things. So let's talk about notation and talk about the derivative of x and the derivative of y. So this notation is Leibniz notation, and he says that this notation means the derivative of x with respect to x. Well, you could almost think of that as this, dx over dx, and that is equal to 1. We also know that the derivative of x is equal to 1 because that coefficient in front of x is a 1, and the slope of that line is a 1 is at any point. So we do use Leibniz notation to support us. Technically, this is not a fraction that can be reduced, but Leibniz notation is very suggestive and it's very, very helpful. Okay, let's go ahead and take a peek at the next one. The derivative of x squared with respect to x. Well, all along, we said that that was just equal to 2x, but we've been keeping a step out of that. It's really 2x multiplied by the derivative of x with respect to x, but like we just said, that is equal to 1, so it is just 2x. Now things are going to change over here to the right. How about the derivative of y with respect to x? Well, that is just dy dx. How about the derivative of y squared with respect to x? Now this is new. We will treat this as a chain rule. Think of this as something squared. So it is 2 something multiplied by the derivative of that something. So this could really be anything, okay? And if it's an x, of course, the derivative of x is just 1, so we would leave it alone, okay? Let's try one here, the derivative of e to the 5x with respect to x. Well, that's equal to itself, e to the 5x, multiplied by the derivative of the something, which is 5, and then we could take the derivative of x with respect to x. Of course, we know that that is 1, so it's just 5e to the 5x. Okay? Now, let's look at the difference. What if we have the derivative with respect to x of e to the 5y? Well, the derivative of e to the something is e to the something multiplied by the derivative of the something. And the derivative of 5y is 5 times the derivative of y with respect to x. So that's equal to 5e to the 5y dy dx, all multiplied together. So we do need to make sure we understand that. We will kind of simplify and mention if we come up with a y, we will always multiply by dy dx. Let's take a look at this detailed example of implicit differentiation. We're asked to find dy dx for this equation. Now, normally you would think we would have to solve for y before we found the derivative of y with respect to x, but now we introduce implicit differentiation. So step number 1 is to take the derivative, and each time the derivative of y is involved, we will include a dy dx. So let's go ahead and do that. Y squared, the derivative of y squared is 2y multiplied by dy dx minus, and now we have the derivative of 5x cubed. We have 15x squared. Now, normally we would write dx, but the derivative of x with respect to x is just 1, equals, and the derivative of 3y is 3 dy dx. Okay, let's look at step number 2. Gather all terms with a dy dx on the left side and everything else on the right side. And this is important because we have this term and this term that need to be together on the same side of the equation. So we have 2y dy dx minus 3 dy dx equals, and we'll add 15x squared to both sides, equals 15x squared. Now, why did we do that? Why did we gather all terms with a dy dx on the left side? So we could factor it out. So we're going to factor a dy dx out of all of the terms on the left-hand side, and we will come up with 2y minus 3 equals 15x squared. So we're getting very close. To solve for dy dx, we just divide both sides by 2y minus 3. So that is your first time to differentiate implicitly, and I think you may have the hang of it, but let's go ahead and practice some more. Okay, let's look at number 1 here. Anytime we come across a y, we will make sure, anytime we come across a y taking the derivative, we will make sure we use a dy dx. Each time the derivative of y is involved, not just a y, not if you see a y. Okay, so here we go. The derivative of y cubed, and we're trying to find dy dx, is 3y squared dy dx minus 2 is equal to 4x cubed plus 2 dy dx. Okay, our terms that have a dy dx in them have to be on the same side of the equation. So we have a 3y squared dy dx minus 2 dy dx. Let's bring this negative 2 to the other side as a positive 2 plus 4x cubed. We're getting very close because now we will gather like terms and we will factor a dy dx out of both terms, and we're left with a 3y squared minus 2 equals 2 plus 4x cubed. One more step, dy dx is equal to 2 plus 4x cubed divided by 3y squared minus 2. Okay, let's be very careful with this next example. What I want you to notice is that we actually have a product rule embedded inside of a chain rule. So we just will follow our same method. Let's give it a try. The derivative of the sine of something, pretend like it's just nothing there. The derivative of the sine of something is the cosine of something. Remember, we leave that inside alone, but now we have to take the derivative of the inside. And that inside function is a product, okay? Maybe I'll change this little note here to a product. Okay? Now, what is the derivative of x times y? The derivative of x times y is, and we always start with the derivative of x, and the derivative of x is 1 multiplied by just y, plus, now we write our x and we take the derivative of y. Now I'm going to show you something. Normally you would say dy dx, but we also know that dy dx is equal to y prime. So why don't we try using y prime? It saves you a little bit of time. It looks a little bit nicer, but I warn you, it is not y to the first power. So make sure you angle it. And we don't usually use a first power anyway, but I just want to make sure you know that we will use y prime here, and feel free to use either. Okay, the right-hand side of the equation, the derivative of 10x is just 10. Now, we have to gather the terms with a y prime in it. And if you notice, where is that? There's only one right here, and we have to get to that. We actually have to get to that term. So how are we going to do that? The first thing I'm going to do is divide both sides by the cosine of xy. So we have y plus xy prime is equal to 10 divided by the cosine of xy. Okay, we're getting close. Let's subtract y from both sides. So we have 10 divided by the cosine of xy minus y. Now things are looking a little bit jumbled up, a fraction minus y. Why don't we change this to 10 secant of xy? And that looks a lot nicer. So the only thing I did in that step was to change 1 over the cosine of xy to the secant of xy. And what's the good news? All I have is one step left, and that is to solve for y prime. And we will divide every term by x. So I'm just going to write 10 secant of xy minus y all over x. And that is y prime, found using implicit differentiation. Okay, let's go ahead and see if we can find the derivative at a point. So what we're giving here is to find the equation of all tangent lines for x squared plus y squared equals 4. You should recognize this. This is a circle with radius of 2 centered at the origin. So x squared plus y squared equals 4 is something that you should recognize is the equation of a circle. Okay? So we want to find the equation of all tangent lines when x is 1. So why don't we take this one step here? When x is 1, looks like there's that. And when x is 1, whoops, we also have a point here. So let's go ahead and draw some tangent lines there. See if I can do a good job here. And I will draw another tangent line. So as you can see, we're going to have 2 lines. It might be nice to label those points. This is 1 comma something, and we need the y value there. So when x is 1, y is plus or minus root 3. So we have a positive root 3 and a negative root 3 here. I have set myself up for the equation of both of my lines already. I have 1 root 3, and I need to find the slope. And then I have 1 negative, or the opposite of root 3, and I need to find that slope. Now the slope there is going to be our derivative at each one of those points. So let's use implicit differentiation. So I will rewrite that equation here. We have x squared plus y squared equals 4. The derivative is 2x plus 2y, y prime. Remember, 2 goes in front, y to the first power, remember that, times the derivative of y equals 0. Okay? We are trying to isolate this term right there. So I'm going to subtract 2x from both sides. And then I'm going to divide both sides by 2y. So that leaves just x over y. Wish I could write that a little bit clearer. So y prime is equal to x over y. And I think that would be a negative x over y. Okay? So y prime here is the opposite of x over y. So that's equal to the opposite of 1 over root 3. And then y prime here for our second point is the opposite of x over y, and that's equal to the opposite of negative 1 over root 3, and this is just 1 over root 3. Okay, now we're all set up to write the equation of our lines. So we have y minus the y value equals the slope x minus the x value, and we can actually just leave that like that. Here we go, y minus the x value, the y value, equals the slope x minus the x value. Okay, the last example, and those are our equations of our lines. And those are both of those lines over here on the right on our sketch. Okay, now let's go ahead and take a look at horizontal and vertical tangent lines. Keep in mind that when we're looking for a horizontal tangent line, that is when the slope, or in calculus, the derivative, is equal to 0. And a vertical tangent line exists when the slope is undefined. Okay, so here the slope is 0. For undefined, you might have a vertical tangent line, or you could have a cusp. Okay, so let's try number 4. Find all horizontal tangent lines of the graph 3x squared plus 2y squared equals 16. Well, let's go ahead and find the derivative and set it equal to 0. So our first step would be implicit differentiation, which is 6x plus 4y y prime equals 0. Well, we go ahead and solve for y prime. So we want to set y prime equal to 0. So we need to go ahead and solve for y prime. So we end up with 4y y prime equals a negative 6x. And then we have y prime equals a negative 6x over 4y. And that reduces to a negative 3/2 x over y. So we're going to set that equal to 0. Actually, I could do that right here. And now, for a horizontal line, setting this equal to 0, the only way that this can equal 0 is if x is equal to 0. But what I like to do is when you're setting an equation equal to 0, a rational expression equal to 0, we only care about the numerator. So it's only when that numerator is equal to 0. So we'll go ahead and say that 0 is equal to 3x, and dividing both sides by 3, x is equal to 0. So now what we have to do is when x is 0, we want to find out what y is. So if you have a horizontal tangent line, the equation is always y equals something. So we're going to take x equal to 0 and plug it in to our original equation. We get 3 times 0 squared plus 2y squared equals 16. So 2y squared equals 16. Y squared equals 8. Y equals plus or minus the square root of 8, which is plus or minus 2 root 2. And there you have it. Those are the two horizontal tangent lines of that graph. Now, vertical tangent lines. Let's talk about that. Our vertical tangent line, we've already found y prime. This is the same graph. Both of these are 3x squared plus 2y squared equals 16. So we have, and I'm going to put from number 4, we have y prime is equal to a negative 6x over 4y. And y prime is undefined when 4y is equal to 0. So when we look for rational expressions and where they are undefined, we set that denominator equal to 0. And again, that negative in front of that 6x can go with either one of those. I can take it with the denominator. It's not a problem. Or you can actually go back and take this with the numerator. Didn't change anything in this problem, but you would have to take it with one or the other. Okay, so divide both sides by 4 and we get y equal to 0. Okay, so now we're going to go back to our original equation and we're going to put y equal to 0. So we have 3x squared plus 2 times 0 squared equals 16. 3x squared equals 16. X squared equals 16 over 3. So x is equal to plus or minus root 16 over 3. So x is equal to plus or minus 4 over root 3. And those are vertical lines. Remember, our vertical lines are x equals something. And that concludes this topic.